Hey there, 10th graders. Welcome. I am just incredibly excited to have you here today. Look, we are going to completely dismantle any math anxiety you might have about this chapter. We are going to build an unshakable, ground-up conceptual mastery of areas related to circles. Okay? Let's dive right into this. We aren't just going to memorize textbook formulas today. No way. We're going to look at the underlying logic, the actual geometry of why these shapes behave the exact way they do. By the end of this explainer, you are going to see circles in a completely new, totally intuitive light. All right, so let's start with a fundamentally simple question. You already know that the area of a complete full circle is pi r squared, right? You've known that for years. But what if we don't want the whole circle? What if we just want a specific piece of it? How do we find the area of just one single slice without having to blindly memorize some complicated new formula? Well, the secret is deeply understanding the why behind the shape itself. To do that, we first need to agree on what kind of slice we're actually talking about. Notice how when you take a slice right out of the center point O out to the edges A and B, you get what mathematicians call a sector. I want you to literally imagine a classic slice of pizza. That angle right there at the center, angle AOB, is usually called theta. The smaller pizza slice is your minor sector. But hey, don't forget the rest of the pizza left in the box. That massive, unshaded leftover piece, that's called the major sector. Both are sectors because they both originate exactly from the center point. Now contrast that with this completely different kind of cut. This one is called a segment. Imagine a perfectly circular cookie, and you take a straight knife and just chop off the edge. You aren't cutting from the center anymore. You're cutting straight across the circle using a line segment, called a chord, which is labeled here as AB. The little edge piece you chopped off is the minor segment, and the giant piece of the cookie left behind is the major segment. Getting this visual difference locked in your head is absolutely crucial for your conceptual clarity. A sector is a center cut. It radiates outward like a fan or a pizza slice. A segment is a chord cut. It's just slicing off the perimeter. They look different, and as we're about to see, the way we calculate their areas is different, but entirely logical. So let's tackle the sector first. We're going to use something called the unitary method, which honestly is just the logic of a fair share. Imagine the whole pizza is 360 degrees, right? And we know the area for all 360 degrees is pi r squared. So if we just wanted a tiny microscopic sliver of pizza that is exactly 1 degree wide, its fair share of the area would just be pi r squared divided by 360. Take a second to visualize that tiny 1 degree sliver. Now, if our actual pizza slice has an angle of theta degrees, say 30 degrees or 45 degrees, we just take that 1 degree sliver and multiply it by theta. And boom, just like that, the formula is unlocked. The area of a sector is simply theta divided by 360 multiplied by pi r squared. Now, what's really amazing here is that it proves you never needed to rote memorize this formula in the first place. It is pure logic. Any sector with an angle theta is just a fractional piece, a fair share percentage of the total 360-degree circle. It's truly brilliant in its simplicity. Okay, let's actually apply this beautiful logic to example 1 from your textbook. Let's step up to the whiteboard here. If we have a circle with a radius of 4 centimeters and a minor sector angle of 30 degrees, we simply substitute those values into our fair share fraction. Our angle theta is 30, so our fraction is 30 out of 360. We multiply that by pi, which we'll use 3.14 for here, and then multiply by the radius squared, which is 4 times 4. Let's walk through the math step by step. 30 over 360 simplifies perfectly down to 1 over 12. When you multiply 3.14 by 16 and then divide by that 12, you get 12.56 divided by 3. This gives us a final minor sector area of approximately 4.19 square centimeters. See? Simple, intuitive, and perfectly logical. But hey, what about the rest of the circle? The major sector? Well, if the whole circle is 360 degrees and our minor sector took up 30 of those degrees, the leftover angle is just 360 minus 30, which is 330 degrees. We just apply the exact same unitary method. Our fair share fraction is now 330 over 360 multiplied by pi r squared. When you run those numbers, you find the major sector is roughly 46.1 square centimeters. So sectors are easy. But what about segments? Remember that cookie edge cut by a straight chord? To find the area of a segment, we use an incredible visualization technique I like to call the segment subtraction trick. Imagine taking the whole pizza slice, the entire sector, and then literally taking a knife and chopping away the triangle piece that sits closest to the center. What's left behind? The segment.
So the area of a segment is just the area of the sector minus the area of the triangle.
All right, let's level up. I like to call this the boss level problem. Example 2. Here, we need to find the area of this light blue segment, ABY. The radius is 21 centimeters. But notice that central angle AOB. It's a wide 120 degrees. Now, this is genuinely a bit intimidating because finding the area of a 120-degree triangle isn't exactly something we do every day.
I know this looks tough, but we have a rock-solid game plan. Step 1, we're going to find the area of the entire large sector, just like we did before. Step 2, we'll put on our detective hats and figure out the area of that tricky 120-degree triangle. And step 3, we execute the subtraction trick. Sector minus triangle equals segment. Let's get to work. Step 1 is a breeze because we've already mastered it. The total sector area is our fair share fraction, 120 degrees out of 360 degrees. That reduces nicely to 1/3. So it's 1/3 multiplied by pi, we'll use 22/7 for this one, multiplied by the radius squared, 21 times 21. When you cross-cancel the 7 and the 3 with a 21, the math is just beautiful. You're left with exactly 462 square centimeters for the total sector. Now for step 2, the tricky triangle. A 120-degree triangle is hard to work with because our standard area formula is 1/2 base times height, and we don't know the height, nor do we know the straight base AB. So imagine putting a magnifying glass right down onto this triangle. What if we drop a perfectly straight perpendicular line down from the center O to the base AB? Let's call that meeting point M. Because the two radii are equal, this perpendicular line perfectly splits the giant 120-degree triangle into two identical, symmetrical 60-degree right triangles. We just unlocked basic trigonometry. Let's zoom in on just one of those right triangles, triangle OMA. We know the hypotenuse, OA, is 21 centimeters. We need to find the height, OM. From our 60-degree angle at the top, OM is our adjacent side. And remember your trig ratios from earlier this year. What connects adjacent and hypotenuse? Cosine. So the cosine of 60 degrees equals our unknown height, OM, divided by our hypotenuse, OA.
And this brilliantly illustrates the power of trigonometric ratios. We know from our trig tables that the cosine of 60 degrees is exactly 1/2. So OM over 21 equals 1/2. We multiply both sides by 21, and our triangle's height, OM, elegantly simplifies down to 21/2 centimeters. See, we have our height.
Next up, we need the base of our big triangle. Let's first figure out the base piece of our small right triangle, which is AM. From our 60-degree angle, side AM is the opposite side. What connects opposite and hypotenuse? Sine. So the sine of 60 degrees equals AM divided by the hypotenuse OA. We know the sine of 60 degrees is the square root of 3/2. So AM over 21 equals root 3/2. Multiplying the 21 across reveals that AM is 21 root 3/2. But wait, remember, AM is only exactly half of our full triangle's base. To get the full base AB, we have to double it. The 2's cancel out perfectly, meaning the full base of the large triangle is simply 21 root 3 centimeters.
Whew, the hard work is basically done. We've deduced our base is 21 root 3, and our height is 21/2. We just plug these into the classic area of a triangle formula, 1/2 times base times height. That's 1/2 times 21 root 3 times 21/2. Multiplying the numerators and denominators gives us a final triangle area of 441 root 3/4.
Finally, step 3, let's bring it all together. We execute the segment subtraction trick for example 2. We take our total sector area, which was 462, and we literally subtract our triangle area, which is 441 root 3/4. That expression right there is the exact area of the segment. You guys just dismantled the most complex problem in the chapter by breaking it down into simple, logical pieces. What an incredible triumph.
Just look at how far we've come. The crucial takeaway here is that there's absolutely no magic happening. There are no arbitrary rules you must blindly accept. It is just logical fractions based on a 360-degree circle and an intuitive visual trick of subtracting a triangle from a sector. Honestly, if you can visualize the shapes, the math pretty much writes itself.
Now it's your turn to apply this out in the real world. Think about this classic textbook problem. A horse is tied to a peg at the corner of a square grass field using a 5-meter-long rope. If that horse walks as far as it can in every direction while keeping the rope tight, what invisible shape is it actually grazing? And knowing that the corner of a square is 90 degrees, how will you find the exact area of that grazed grass? I'll leave you to think about that fair share fraction. Keep breaking down these problems, stay incredibly curious, and keep visualizing the math. Okay, welcome everyone to this exclusive explainer. If you're a 10th standard student gearing up for the Karnataka SSLC board exams, specifically subject code 81E or 81K, you are in exactly the right place. Today, we're not just reviewing basic textbook concepts, we're actually looking at the ultimate blueprint. This is your playbook for cracking Chapter 11, areas related to circles, straight from the perspective of the people who actually grade your papers. So let's dive right in. For the next few minutes, I want you to think of me as your veteran board exam evaluator. I evaluate thousands of SSLC math papers every single year. I know the official marking scheme completely inside and out, and honestly, it breaks my heart to see brilliant students just throwing away free marks in this specific chapter. You already know what a radius and a circle are. We're definitely not wasting time on that. Instead, I'm going to reveal the exact secrets of the official key answers so you can maximize your score.
Here is our roadmap for today. We're going to start inside the evaluator's mind, hit the 1-mark formula goldmine, crack the 2-mark arc questions, conquer those heavyweight 3-mark shaded regions, and finally, avoid the deadly exam mark traps.
Okay, Section 1. The 1-mark formula goldmine. This is the absolute easiest place to secure marks on your paper because it relies entirely on the direct application of fundamental textbook formulas. Now, I want to share a really powerful visual memory trick. We have the formula for the length of an arc, theta over 360 multiplied by 2 pi r, and then the area of a sector, theta over 360 multiplied by pi r squared. Notice how the base fraction, representing the angle out of 360 degrees, is literally identical. The only difference? For the arc length, think of it as the crust of the pizza. You multiply by the circumference. For the sector area, the whole slice, you multiply by the area of the circle. Memorizing this visual symmetry, it's a lifesaver. It completely prevents exam panic.
Now, you might be wondering, okay, I know the formulas, but how is this actually tested? Great question. How does the board test this in your 1-mark multiple choice section? Well, they almost never ask you to simply plug in the radius and the angle. No, they want you to work backwards.
And this brilliantly illustrates that exact trap. This is a direct pull from a past official exam. They give you the arc length, which is 4 pi centimeters, and the radius OB, which is 9 centimeters, and they ask you to find the angle, theta. Now, students usually panic here because the unknown is right there in the numerator of the fraction. But as an evaluator, I'm just looking to see if you stay calm. Do you write down the baseline arc length formula? Plug in 4 pi on one side and 9 for the radius? If you do, the pi cancels out beautifully on both sides, leaving you with a really simple algebraic step to find that 80-degree angle. Recalling the baseline formula exactly as written is your ultimate shield against these displacement traps.
Let's see how this builds into Section 2, cracking 2-mark art questions.
Here, the difficulty steps up just a little bit. This is the written section, and examiners specifically want to see your mathematical logic unfold step by step. So the absolute crucial point is how we distribute those 2 marks. Take a look at this official marking scheme table. I literally cannot stress this enough. Half a mark is awarded simply for writing the correct formula. Another half mark is awarded the exact moment you substitute the given values into that formula correctly. Even if your final calculation goes completely off the rails because of some silly multiplication error, you've already secured 1 out of 2 marks just by writing the formula and plugging the numbers in. So whatever you do, do not leave the page blank. Let's break down this specific past paper diagram. The arc APB is given as 22 centimeters, and let's say the angle theta is 60 degrees. The question asks for the radius r. According to our official key answers, the moment you write length of arc equals theta over 360 times 2 pi r, boom, you get a half mark. The moment you write 22 equals 60 over 360 times 2 times 22 by 7 times r, that's another half mark. You've just grabbed 50% of the credit before even doing any hard math. This is exactly how you play the evaluator's game. All right, now we reach the climax of our explainer. Section 3, the 3-mark shaded regions. This is an absolute favorite for the examiners. These are the heavyweight questions that really separate the average students from the toppers. You flip the page and you see this, the infamous rectangle inscribed in a quadrant. It looks super intimidating, right? But as an evaluator, I'm going to tell you a secret. To me, this isn't some complex geometry problem. It's really just a simple 3-step subtraction problem. That's the whole shebang. You find the area of the big shape, find the area of the unshaded inner shape, and just subtract them. Here is exactly how the official key answers map out the marks. Step 1. Write the area of sector formula and solve it. That's a half to 1 full mark. Step 2. Calculate the area of the inner shape, in our recent example, a rectangle, using length times breadth. That gets you another half mark. Step 3. Show the clear subtraction step and write the final answer with its units. Now, huge warning here. Never ever combine these into one giant messy equation. Keep step 1 and step 2 completely separate on your paper so I can easily find them and give you those half marks. And speaking of the final answer, look at this number. 462 centimeters squared. This is the sample final answer straight from a board key for a shaded region question. Notice what's sitting right at the end? The squared symbol. If you just write 462 centimeters instead of 462 centimeters squared for an area question, the official marking scheme mandates that we deduct a heartbreaking half mark. Imagine doing all that complex math perfectly and losing credit over a tiny number 2? No way. Don't let it happen. Which brings us seamlessly to our final synthesis section. Deadly exam mark traps. This is all about error prevention and safeguarding those hard-earned half marks we've been talking about. Take a look at this comparison. We have a typical mark-losing answer up against a perfect board answer. With the mark-losing one, the student clearly knows the math, but they skipped straight to plugging in the numbers. They wrote 22 by 7 times 14 squared. They probably think they're saving time. But the perfect board answer? The topper explicitly writes area equals theta over 360 times pi r squared before doing any math. The evaluator instantly gives the formula half mark for that explicit step. The rushed answer runs the massive risk of losing it entirely if their final calculation is wrong, so always be explicit. I want you to burn this checklist into your memory before you walk into the exam hall. Here are my rapid-fire traps. Number 1, skipping the base formula step. We just covered why that's literally deadly. Number 2, forgetting to use pi as 22 over 7 when substituting. You know, the board usually designs the radius to be a multiple of 7, so it cancels out beautifully. Number 3, missing the squared units for area. And number 4, doing multi-step calculations in one single line. Don't do it. Break it down, show me your steps, make it incredibly easy for me to give you marks. So, as we wrap up this masterclass on Chapter 11, I want to leave you with this final thought. When you sit down with that exam paper, are you going to leave half marks on the table by rushing and combining steps? Or are you going to play by the evaluator's rulebook, structure your answers logically, secure those formula marks, and maximize your final SSLC score? The choice and the marks are entirely in your hands. Thank you so much for joining me for this explainer, and best of luck on your exams. You've got this.